Hi guys, in the last lecture we studied about the inductance of a conductor. So we first saw internal inductance, which was mu naught mu r by 8 pi Henry per meter. Then we saw external inductance, which was mu naught mu r by 2 pi ln d by r Henry per meter. Then we saw total inductance, which was mu naught mu r by 2 pi ln d by r prime Henry per meter, where r prime is GMR, which is equal to 0.7788 R. Then we saw inductance of two wire line, that is mu naught mu r by pi ln d by under root r1 prime and r2 prime. This was the GMR of the system. It was geometric mean of GMR of first conductor and GMR of the second conductor. And then we saw the flux linkage. Flux linkage of a conductor in a group. Lambda was sigma k equal to 1 to n mu naught mu r by 2 pi ik ln 1 by d ik. This was the flux linkage of conductor I in a group of n conductors. Okay, so that is what we learnt in the last lecture. In this lecture we will be focusing on removing the disadvantage of the stranded conductor, that was the corona loss. So we saw that stranded conductors were having a non-uniform surface. Okay, so we removed the disadvantage of tensile strength using our ACSR conductor. So let me recap it for you, what kind of conductors we saw. First we proceeded from solid. So there we had a problem of skin effect. To remove that we moved to stranded. There we had a problem of tensile strength. Then we moved to composite stranded. So there we had a problem of corona. So we have to remove this problem of corona, or we have to reduce it. One way of reducing it was that we saw we use expanded ACSR, but that does not completely rectify the problem, or it does not reduce the corona to a low extent. Okay, corona is still there and it is quite high. So why is corona present in stranded conductor? Due to the non-uniform surface. Now to reduce corona loss, we have to reduce the electric field. To reduce electric field, we have to increase effective radius. That is, we have to increase GMR. Or other way is to increase GMD. But to increase GMD, distance between the conductor, that is DAB and DAC, these must be increased. To increase distance between the conductor, cross arm length of tower must be increased. Cross arm is like this. So this is the length of cross arm. This must be increased, but any modification in the design of tower is highly unrecommended because it increases the cost of the system. So we cannot increase GMD, we have to focus on GMR. Now this GMR can be increased by means of bundled conductors. That is why we move from standard conductor to bundled conductor, to reduce the corona loss, as they increase the effective radius and thus they reduce the electric field, because electric field is lambda by 2 pi epsilon naught r. So they reduce the electric field by increasing the effective radius and hence corona loss reduces. So as the name suggests, bundled conductor, there are bundle of conductors, that means more than one conductor per phase. So usually what happens is, three-phase conductors are located at three corners of a triangle. That is called as single conductor system. Why single conductor? Because there is one conductor per phase. Now if you replace each conductor by a group of two conductors, like A phase has two conductors, A1 and A1 dash, B has two, B1 and B1 dash, C has two, C1 and C1 dash. So then it is called as a bundled conductor. Now how do they reduce corona loss? One possible explanation is, now current in A1 will be IA by 2, A1 dash will be IA by 2. Since current is reduced to half, current density will also become half. Electric field, which is equal to J by sigma, will also become half. Since electric field becomes half per conductor, that means corona loss reduces. This is just one way of explaining. We will explain it in terms of GMD or GMR to get a better understanding how the corona loss is reduced in case of bundled conductor. But just to now understand that if the current density is divided, current density reduces, effective current density, that means electric field will go down and hence the corona loss will also be reduced. Now let us focus on one group of conductors. Let us say this is A1 and this is A2. This conductor has a radius R1, other has a radius R2. Now if I want to find flux linkage of A1, it will be mu naught mu R by 2 pi IA1 ln 1 by d A1 A1 plus IA2 ln 1 by d A1 A2. Now since these two are part of a single conductor, each will be carrying a current I by 2. So we can write it like this: mu naught mu R by 2 pi I by 2, 1 by d A1 A1 is R1 prime, I by 2, 1 by S. So mu naught mu R by 2 pi, take I common, it will be ln 1 by under root R1 dash into S. R1 dash into S occurs because these logs get added, and under root because of this 2. So now if you see, earlier in case there was only a single conductor, then flux linkage would be dependent on ln 1 by R1 dash. But now R1 dash is replaced by R1 dash into S. Now what happens when multiple conductors are present in a single phase? There will be two types of flux: self flux for each conductor and mutual flux between the two conductors. So here A1 and A2 will also have some mutual flux, but this mutual flux is between the conductors of the same phase. So we can neither call it self flux completely or nor we can call it mutual. It is mutual flux for the two conductors, but for us, if we look out from the phase perspective, it is the self flux because it is within the phase. Okay, that is why we cannot call this distance as GMR. We call it as self GMD. Self geometric mean distance is under root R1 dash S, because GMD signifies mutual flux and self indicates that this is the mutual flux within the same phase. That is why self GMD. Now obviously this distance S is greater than R. Okay, so under root R1 dash into S is greater than under root R1 dash into R1 dash. So that means self GMD is greater than GMR. So here thus we have increased the effective radius. Again here self GMD signifies if we want to replace these two conductors by a same conductor, single conductor, and still have the same amount of flux linkage, then that should have a radius of under root R1 dash into S. That is what self GMD signifies. So that means the effective radius of the system is increased, due to which electric field will go down and corona loss also reduces. So that is how by the use of bundled conductor we increase the GMR, as it is now GMD. But if we want to calculate self GMD for the entire system, as we saw in case of two wire line GMD system, or let us say self GMD system, will be geometric mean of GMD A1, GMD A2. GMD A1 is R1 dash into S, R2 dash into S. So it will be S under root R1 dash R2 dash half. So that will be the self GMD of the system. In case R1 dash equal to R2 dash equal to R dash, then self GMD becomes under root R dash into S. So that is for the system. Whenever you are calculating GMD, self GMD or GMR of a system, just take the geometric mean of individual conductors. Okay, that is what you have to do in each and every case. That is why it is known as geometric mean distance or geometric mean radius. Now let us determine the inductance for the case of bundled conductor. So what I have done is I have taken a single phase 2-wire line. Okay, then what I am doing is I am replacing this forward conductor by a group of n conductors and this return conductor by a group of m dash conductor. Earlier it was carrying a current I, this one was carrying minus I. So current per conductor would be I by n, I by n. Similarly here current per conductor would be minus I by m dash, minus I by m dash, like that. Now if first of all to find the inductance we need to find the flux linkage. So to find the flux linkage of a conductor in a group, let me choose a conductor here, let us say ith conductor. Okay, so lambda I would be mu naught mu r by 2 pi. So first let us see the flux linkage due to conductors in forward group. I1 ln 1 by di1 plus in ln 1 by din. And remember, dii whenever it will occur, it will be equal to ri prime. Now let us take from the other group mu naught mu r by 2 pi I 1 dash ln 1 by d I 1 dash. Similarly up to m dash ln 1 by d I m dash. Okay, now we know the currents I1 up to In are equal to I by n and I1 dash up to Im dash are equal to minus I by m dash. So lambda I will be equal to mu naught mu r by 2 pi I by n 1 by d I1 1 by d In minus mu naught mu r by 2 pi I by m dash 1 by d I1 dash ln 1 by d Im dash. Now these logs can be added. Mu naught mu r by 2 pi I by n ln 1 by di1 di2 up to din and minus mu naught mu r by 2 pi I by m dash ln 1 by di1 dash I2 dash up to dim dash. Now suppose if we want to combine these two terms but their coefficients are different, so let us take this 1 by n and 1 by m dash into the power. So what will happen is lambda I mu naught mu r by 2 pi into I, the first term will be ln 1 by di1 up to din raised to power 1 by n 1 by di1 dash dim dash raised to power 1 by m dash. Now if we combine these two logs, what I will get? mu naught mu r by 2 pi I ln di1 dash I2 dash im dash raised to the power 1 by m dash di1 I2 up to in raised to the power 1 by n. So this will be the flux linkage. Now to find the inductance, we have to divide lambda I by II. Current in each conductor is I by n. So that means it will become mu naught mu r n by 2 pi ln di1 prime di2 prime dim prime raised to power 1 by m prime I2 up to din raised to power 1 by n, this one. Okay, but this is the inductance of one conductor out of n conductors. Same way we will have n inductances for n conductors, but it would be difficult to analyze n inductances, one for each conductor. So it is better that we replace all the inductances by a single value, that is their average. So if I want to take the average of all the inductances in a single group, so what will happen? L average can be computed as I is equal to 1 to n Li by n. So if I divide it by n, it will become mu naught mu r by 2 pi sigma I is equal to 1 to n ln di1 dash I2 dash up to d im dash raised to power 1 by m dash. Remove it from here. di1 di2 up to din raised to power 1 by n. Okay, now whenever the logs are added, their arguments are multiplied. So we can replace it like this. Multiplication can be represented as pi, then di1 dash I2 dash up to d im dash raised to the power 1 by m dash divided by di1 di2 up to d in raised to the power 1 by n. So that is the average inductance of each conductor. Now what happens is, actually in case of bundle conductor, we have replaced a single conductor by a group of conductor. Suppose earlier there was one conductor between point A and point B. Now I have replaced it by multiple conductors like this. But effectively all these conductors are connected in parallel. So if we want equivalent inductance, then we will suppose each inductance is L, then equivalent will be when n inductors are connected in parallel, L by n. Now that is why I was trying to find the average, because while taking the equivalent, we can say that each inductor has equal inductance, which is equal to L average. That means inductance of forward path will become L average by n. In the formula, this n can be raised as power pi I is equal to 1 to n di1 dash I2 dash up to im dash raised to power 1 by m dash n di1 I2 up to in raised to power 1 by n square. Here pi indicates multiplication of n terms like these. Okay. So this inductance of forward path is written as mu naught mu r by 2 pi ln mutual GMD by self GMD. Now this mutual GMD is nothing but I1 dash I2 dash up to Im dash raised to the power 1 by m dash n. If we expand this, it will be, first take I equal to 1, 1 1 dash 1 2 dash up to 1 m dash. Then take it up to n, n1 dash n2 dash up to nm dash raised to the power 1 by m dash n. Now see, in each bracket we have m dash terms. And how many brackets are like this? 1, 2, 3 up to n. So total terms will be m dash into n. The same we are raising the 1 upon power. Okay. Power is equal to 1 upon number of distances inside the bracket. That means it has the units of a distance. Similarly, we can expand self GMD. GMD self is di1 I2 up to in raised to power 1 by n square. This can be expanded like 1 1 1 2 1 n n1 n2 nn raised to power 1 by n square. Now if you see, in each bracket we have n terms and we have n brackets like this. So we have n square terms and we are raising to the power 1 by n square. So this also has the units of distance. But here if you see, the distances are within the same group, like 1 and 1, 1 and 2, 1 and n. But 1 and 1 dash are the conductors belonging to two different groups. That is why it is called as mutual GMD. This is called as self GMD. But there is no need to remember these formulas. Let me tell you how to derive this self and mutual GMD easily. Suppose there are 3 conductors in forward path and 2 conductors in return path. They have a distance d, d, d. This is the distance capital D. Let us number this 1 2 3 1 dash 2 dash. Now first of all, about mutual GMD. Then we will take first d1 1 dash 1 2 dash, then take 2 1 dash 2 2 dash. Similarly take 3 1 dash 3 2 dash. How many terms are coming inside? 6. So raise it to the power 1 by 6. Here n is equal to 3, m dash equal to 2. 1 by m dash n is 1 by 6. d1 1 dash. How much distance is between 1 and 1 dash? d plus 2d. 1 2 dash. How much distance is there? d plus 3d. Then 2 1 dash. How much distance? d plus d. 2 2 dash, d plus 2d. Then 3 1 dash, d 3 2 dash, d plus d. So that is how you calculate the mutual GMD. Now since mutual inductance M12 is equal to M21, so whether you calculate mutual GMD from the forward path or from the reverse path, it will be same. How? Suppose I was calculating mutual GMD from the return path. Then how will I take mutual GMD from the return path? We will take d 1 dash 1, 1 dash 2, 1 dash 3. Take combination of one conductor with all the conductors of the other group. Then proceed to the next conductor, 2 dash 1, 2 dash 2 and 2 dash 3. Again raised to power 1 by 6. 1 1 dash is same as 1 dash 1, 1 dash 2 is same as 2 1 dash, 1 dash 3 is same as 3 1 dash. 2 dash 1 is 1 2 dash, 2 dash 2 is 2 2 dash, 2 dash 3 is 3 2 dash. So mutual GMD of forward and return path is same. Now let us take self GMD of forward path. Here you have to take combinations within the same group. So first take combination of 1 with all the conductors in the same group, 1 1, 1 2, 1 3. Then for second, 2 1, 2 2, 2 3. Then for third, 3 1, 3 2, 3 3. How many terms are coming? 9. So raised to the power 1 by 9. Now we substitute d11 is r dash, 12 is d, 13 is 2d. Then 21 is d, 22 is r dash, 23 is d, 31 is 2d, 32 is d, 33 is r dash, raised to the power 1 by 9. Okay, that is the self GMD of forward path. Next, let us calculate self GMD of return path. Okay, it will be take 1 dash, 1 dash, 1 dash, 2 dash, then 2 dash, 1 dash, 2 dash, 2 dash raised to the power 1 by 4, because 4 terms are there. So it will be r dash, it will be d, it will be d into r dash. So that way we have to calculate self and mutual GMD. Now while we are calculating the inductances, inductance of forward path will be mu naught mu r by 2 pi ln GMD mutual by DSF, that is GMD self for forward path. Okay, self GMD forward. Then L return will be mu naught mu r by 2 pi ln GMD mutual by DS return. And L system, since it is a single phase 2 wire line which has been broken into 3 and 2 conductors respectively, L forward plus L return mu naught mu r by pi ln, or let me show you how it comes. Log will get multiplied. Let us say GMD mutual is DM, DSF DSR. Again we will take 2 outside. Mu naught mu r by 2 pi ln dm by dsf dsr into 2. This 2 will get cancelled out, so it will come out to be mu naught mu r by 2 pi, sorry, mu naught mu r by pi ln dm by under root dsf into dsr. So if you see, in case of system, the self GMD is geometric mean of GMD of each path, that is forward and return. That is what I was telling you. Whenever you calculate for the system, take geometric mean of each and every path. If there were 3 paths, that is the case for 3 phase, then you have to take cube root of DAB, DBC and DC, like that. That also we'll derive later on, don't worry. Just remember, whenever you are calculating for the system, you have to take geometric mean of each and every path. Now let us see what are the advantages of using bundled conductor. First and foremost advantage, electric field reduces, so corona reduces. Second, inductance is now mu naught mu r by 2 pi ln mutual GMD by self GMD, and we know self GMD is greater than GMR. So inductance reduces, okay, because inside the log the denominator is increasing. Earlier there was GMR, now it is self GMD, and as I proved, self GMD is always greater than GMR, so inductance will reduce. If inductance reduces, omega L, which is equal to reactance, will also reduce. Then voltage drop in the line, which is I into X, will also reduce. That means the voltage reduction that was occurring between sending and the receiving end is now reduced. So we will have higher receiving end voltage, which is always desirable. That voltage drop in the line should be less. Next is capacitance. Capacitance is that we will derive in the later lectures, ln dm by ds. Now this has increased, so capacitance will increase because the denominator of the term is reducing. So capacitance increases, so power factor also increases. Higher the capacitance, better is the power factor. Though there are disadvantages also of increase in capacitance, the thing is line charging current also increases. We will see when we will study the performance of line what is the line charging current. But for now, just understand that line charging current also increases, which is undesirable. But power factor improves, that is desirable. So this is an advantage as well as disadvantage. Okay, so here I am combining all the advantages and disadvantages. It might involve some terms that we will study in later on lectures. Later we will derive the maximum power is Vs Vr by X. As I just told you, X reduces, so Pmax increases. Pmax is directly related to stability. Stability increases. We will derive it in the chapter of stability. As the Pmax increases, stability improves. Next we will derive Zc. Characteristic impedance is L by C for a lossless line. Now inductance decreases, capacitance increases, so Zc reduces. Zc defines some other term, that is SIL, that is surge impedance loading. Zc is also called as surge impedance. So it is called as surge impedance loading, which is Vr square by Zc. As Zc reduces, SIL increases. Now SIL is basically defined as the ideal loading capability of the line. That means you must not put the load more than or less than SIL on the line. Ideally the load should be SIL. So if SIL increases, that means you can put more load on the transmission line, which is always desirable. And next, radio interference is also reduced. Radio interference means interference of power lines with the communication lines. Why is it reduced? Because the current per conductor is reducing, so their flux will reduce. If their flux is reducing, then the EMF induced in telephone line will also reduce. Or otherwise you can say inductance goes down, so lambda, which is equal to Li, also reduces. So it interferes less with the communication line. So these are the advantages of the bundled conductors. Okay. So inside a bundled conductor, if there are two conductors, each conductor will be stranded. Okay, do not think that each is solid. So like this grouping will be there. Each is a stranded conductor, and these two conductors are collectively called as bundled conductor. Okay, so stranded conductor is not eliminated, but rather it becomes a part of bundled conductors. Now let us summarize what we have covered in this lecture. We first saw how to reduce corona loss. So we came out with a theory that we have to increase GMR. Then we saw what are the bundled conductors and how current density is reduced to reduce corona loss. Then we saw how GMR is replaced by self GMD in case of bundled conductor, and self GMD is always greater than GMR. So effective radius increases. Then we derived inductance. Inductance was mu naught mu r by 2 pi ln GMD by mutual GMD by self GMD, and L system was mu naught mu r by pi ln mutual GMD by under root ds1 ds2. Then we saw some of the advantages of bundled conductors. Okay, so that is why the practically used conductors are bundled conductors. In the next class we will see, up to now we have been considering only single phase, how three-phase transmission line conductors are arranged and what are their advantages and disadvantages. That we will see in the next class.